Welcome back. Now let's put some numbers. Let's put some numbers regarding the process. To give us some room, let me delete this. Do you remember the transformer relation between the primary current, the secondary current, N1 and N2? We have N primary, I primary, it's equal to N secondary, I secondary. Is that correct? When I come to CT, we know the ratio. I can have a CT ratio of this one. This will be 1 and 1, CT1. 1 to N2. So when I come to CT1, pay attention. When I come to CT1, I have 1 multiplied by I primary. The primary current comes in, will be equal to N1 time I secondary of CT1. Can you see? This is 1. For CT2, I have the same. I have 1 multiplied by I secondary, which is this secondary, it's equal to N2 I secondary of CT2, which gives me that IP primary and I secondary. If I replace I primary in here and I secondary into this, so I take I secondary, put it back into here, I take I primary into top. This will gives me the following. I have N primary, N1, I secondary of CT1, it's equal to NS, N2, I secondary of CT2. For me to have this current minus this current equals 0, do you understand? I need to get the differential to be 0. Therefore, it's very important for me to find the matching, to find this and this relationship. That's what's known as a matching ratio. You can see it's very easy for me to make sure the system will work if I design the CT, the ratio of this CT, ratio of this CT in conjunction with this ratio. That clearly offer me to have a different, in theory, to have a different current of 0 unless there is an internal fault. And that's what that will happen. I'll protect it if there's an internal fault of the transformer. Is that clear? Guys, I really strongly recommend you to go and read the book, chapter 8, the beginning of it. Because this is gonna make the foundation for us when it comes to 3-phase transformer protection using differential. So please go back and revise the relationship between primary, secondary of the transformer. We've already covered in depth the relation between primary, secondary for the CT current transformer, and I'm pretty sure all of you guys would be able to come up with this logic, this setup. Is that clear? I don't think that will cause major issue for you to determine this. Now, the I differential, I want to call it ID. I want to call it ID. So the differential current, I want to call it ID, which is equal to IS secondary of CT1 minus I secondary of CT2. This is what the relay will do differentiation between the secondary current of CT1 and the secondary current of CT2, and will make sure that the system is in order. And as I showed you before, and primary N1 and secondary N2, this matches perfectly will work. Perfectly will work if this system. If you want this to be equal this, if you want, pay attention, if you want this one to equal this one, you must now make sure to have ID is 0, you must make sure that this equal this. Secondary of CT1 must equal secondary of CT2 for ID to be 0. Therefore, I have now NP N1 equal to NS N2. This would be a perfect scenario if I can achieve this relationship. However, in reality, it's not possible to obtain a CT ratio and a CT and a ratio of the transformer to match percent. That's why I always have to take into consideration an error. An error regarding this. Now, what's an error? Why do we have an error? Number one, the error exists because of CT ratio mismatch. That's number one. Number two, remember the CT chapter? Inside the CT chapter, we clearly explain the CT error. Remember the CT error, the I magnetization divided by I2. Remember this from the previous chapter? This is the second error. So the first error, mismatching error. The second error will be your CT error, and you have stuff called underload depth changer, which is we will explain at later stage. Error and the margin error for the relay, and that's all of it known in your book as a K factor. This is the K factor. Include mismatch error for ratio mismatch error, CT error, underload depth changer error, and a margin error. Okay, that's what they know the factor, the error factor K. Also, we are defining restraint current. In your book, they define the restraint current. The restraint current is equal to I secondary CT1 plus I secondary CT2 divided by 2. That's what they defined, the restraint current. The name came from the electromechanical relay design, where the current produced a restraint torque on the moving disk, while the differential current produced the operating torque. So now the relay will only operate, the relay operate when ID bigger or equal to K IR. This is the condition of operation of a relay. That's why always there's a margin. I hope that explained the initial concept of transformer from a fuse and from a percentage differential.